Hello, and welcome to the second section on the chapter studying exponential and logarithmic functions. This will be a shorter video because in this particular video, we're focusing on the section about graphing exponential functions. And we've already discussed a lot of that in the previous video. So in this one, we'll be focusing mostly on translations of exponential functions, shifting it up, down, left, and right. We'll talk a little bit about what happens as well when you scale it, when you stretch it or compress it. Remember, translations, when you move a graph up, down, left, and right, that does not change the shape of the graph. It's like a sticker. You're peeling it off and putting it down somewhere else. When you stretch or compress, though, you're actually stretching and compressing. That's like a Stretch Armstrong thing. It is going to change the shape of the graph. So let me share my screen with you, and we'll go ahead and get started. So what we're looking at now is we're looking at some of the characteristics of a parent function. And this is what we talked about in the previous video when we were graphing exponential functions. Now, let's remind ourselves what an exponential function looks like. An exponential function is basically y equals some initial value a times some positive number, not 1, raised to the x power. Now, we're going to allow a to be 1. In other words, our initial value is going to be 1. We're going to look at a simplified version of the exponential function, and we'll call this the parent function. So we're going to be focusing on this one that you see right here, outlined in blue. So this is going to be our f of x equals b to the x power. So a, in this case, is 1. So when we're looking at that, we want to talk again about what we have. Our coefficient is 1, so our initial value is 1. The base b must be strictly positive. We don't want square roots of negative numbers. And it can't be 1 because 1 to any power is just 1. It gives us a horizontal line. And that doesn't have the characteristic shape of an exponential. So we eliminate 1 from the possibilities. It is a one-to-one function. What does one-to-one mean? When you look at the graph, these are two different graphs right here. When the value of the base, b, is greater than 1, it's a growth function. And it's increasing like this. So as x moves to the right, it goes up further. So it looks like this. When the value of the base is between 0 and 1, so it's a proper fraction, still positive, proper fraction like 1/2, 2/3, 4/5, something like that. When we have that, it's an exponential decay problem, and it comes down and decreases towards the positive x-axis, coming down like this. When we talk about it being a one-to-one function, what we mean is for every 1 x value, you get 1 y value, and every 1 y value, that's exactly 1 x value. When you look at the function, remember this means it passes both the vertical line test, that tells you it's a function, and a horizontal line test. So that if you cut through it with a horizontal line, you only hit it at most 1. You might miss it totally. Let me show you what I mean by missing. If I were to draw a line horizontal down here, granted my handwriting's not that great, so assume it's horizontal, okay? I don't hit this curve at all because it's approaching the x-axis as an asymptote. But if I put the horizontal line up here, I'm only hitting it 1 point of that value right here. That's what we mean by passing the horizontal line. That guarantees that if it was a function, that it is in fact a one-to-one function. So now what we want to do is we want to look at the next characteristics of our parent function, the b to the x. The horizontal asymptote is going to be y equals 0, which is the x-axis. So when it comes down, when it's a growth function, then it approaches the negative y-axis as x goes to negative infinity. I think I said x axis a minute ago, and I mean y axis. When it is a decay function and it's coming down like this, it approaches the positive x-axis. So x-axis, this is the equation y equals 0, so x-axis. I guess I did say it the right way. The wrong function. All right, so the domain is from negative infinity to infinity. We can use any x value on the real number line as an exponent. So remember, exponents can be anything: positive, negative, rational, irrational, pi, 42, any of those. Base has to be positive and not 1, which means the answer, y value coming out, is going to have to be strictly positive. You can't take a positive number, raise it to a power, and get anything but a positive. You can't even get 0. Now, the next thing that we see is the range is from 0 to infinity. So if it's a growth equation, it's increasing to the right, and if it's a decay equation, it's decreasing to the right. But in both cases, the curve lies entirely, completely above the x-axis, y equals 0. Now, the x-intercept, well, there aren't any. It lies completely above the x-axis, so there are none. Well, the only way to get one is to pull the whole thing down. If we shift it down, if we stretch it like this, so it goes below the x-axis, then we can get an x-intercept. Y-intercept, the normal basic parent function, 1 times b to the x, because the initial value is 1, when x is 0, b to the 0 gives you the value of 1. So it goes through the ordered pair 0, 1, in both the growth and the decay functions. Now, it's increasing. It's a growth equation if the base is a number greater than 1, decreasing if the number is between 0 and 1. It has to be between 0 and 1, not allowed to be 0, not allowed to be a negative, not allowed to be 1. All right, now that we've discussed the parent equations, these are going to be the ones that we're going to be shifting up, down, left, right, and maybe stretching across a little bit. Okay, so let's start with a vertical shift. A vertical shift takes your graph, whatever it looks like. So we've got a graph, and it just moves it up, or it moves it down. But it doesn't change the graph at all. So you're just like peeling off the sticker and sticking it down somewhere else, right? So vertically up or vertically down. Now, in order to do that, you're affecting the y value, and it's not actually inside the main operation. You flip up and down outside the main operation, which here is the exponential. So we simply take the parent function, which is 2 to the x here, and we add 3 to shift it up 3, and we subtract 3 to shift it down 3. Notice what this does to the graph. It is exactly the same graph. I know they won't look the same, but they are in fact exactly the same. Same curvature, same everything. They're like stickers that have been peeled off and set down somewhere else. The difference is this one in red that you see right here is now crossing the y-axis at 4, right? Because the parent function crosses at 1, and you shifted it up 3, so 1 plus 3 gives us 1. 0, 4. Now, what about the one that we pulled down 3? So we took this one and we pulled every y value down 3. That's exactly what we're doing. We're taking each y value and subtracting 3 from it. And so it moved it down 3. So if I take this y value and I subtract 3, I get to here. If I take this y value for the same x, subtract 3, I get to here. That's exactly what we're doing. So this one now crosses down here at negative 2. Why negative 2? Well, the parent function crosses at 0, 1. 1 minus 3 gives me negative 2. Notice that this also shifts the horizontal asymptote. If I shift it up by 3, the new horizontal asymptote is y equals 3. And if I shift it down, the new horizontal asymptote is y equals negative 3. The x-axis, or y equals 0, is the horizontal asymptote of the parent function. Now let's take a look at what happens when we shift it left and right. Again, it's exactly the same graphic, no change in the relationship between the points. We're just peeling it off and setting it down to the right and to the left. So it's just a sticker, and you're removing the sticker, but you're not stretching or compressing the sticker at all. Now, in order to move things left or right, that affects the x. It's found in the exponent. So it's going to be inside the exponential up there in the power next to x. Because it is close to x, it's going to be the opposite of what you would expect. Now up here, notice that the plus 3 moves it up 3, but it's not close to the y. In fact, it's on the other side of the equation. If we move the same side of the equation, we would actually have y minus 3 equal to 2. That would still shift it up 3. But when it's next to the y, it's the opposite of that value. That's the way it moves. So when we have x and it's close to the x value, instead of this plus 3 moving it to the right, the plus 3 will actually move it to the left. Okay? By 3. And here, where we have x minus 3, it means that each value is going to shift to the right by 3. Minus 3, normally we think it'll go left, but in this case, we do the opposite because it's right next to the variable expected. So what does that do to our graph? Well, notice it does not affect the horizontal asymptote at all. Horizontal asymptote stays the x-axis, y equals 0. It does affect the intercept quite a bit, but it's not as easy to figure out what the new changes like before. We're just able to add the shift onto the previous y-intercept. This is the new y-intercept. Here, because we're shifting it left and right, all bets are off because I don't know what this value over here becomes when I shift it left and it's still crossing the y-axis. In order to find it, you're going to have to let x be 0 and compute it in here. So in this case, it would be 2 to the third, which is 8. So our graph is a bit off. Right? So I'm not too happy about that. I also know it's off because this blue one, the parent function, should be going right through this point right here, which is at 0, 1. A little off. So our graphs are, they could do a better job of drawing, right? And then 2x minus 3 is then actually shifted to the right. And to know what the x-intercept is going to be, I have to let x be 0. 2 to the negative 3 is the same as 1 over 2 to the third, which is 1/8. So this orange is crossing the y-axis of the value y. Now we want to talk about shifts of a parent function. If we take constants c and d and we apply them to affect y, which is outside the exponential plus a value of minus value, and then another value to affect x, so it's going to be inside the exponential, which is going to shift it left or right, then we can write down what the effect of these are all in one equation. So if we're looking at parent functions, so we have the parent function right here, y equals b to the x, and now we have a new function, f of x, based on our parent function, which looks like b to the x plus c plus d. What the heck? Right. Well, if c is positive, it'll be plus a number, plus 3. That means it actually went left 3. So when c is positive, then it moves in the opposite direction. So it moves actually to the left that way. Now, if c is negative, it becomes x minus c. So like x minus 2 would actually shift it to the right 2. Okay. Now, what does the d do? The d is not inside the main operation. It's outside the main operation. So it's really affecting the y value. So because it's not on the same side with the y, it's going to do exactly what you think it would. If it's plus 5, it moves up 5. If it's minus 7, it moves down 7. Now, if you have this here on the outside of the exponential, this does affect the horizontal asymptote. The new horizontal asymptote will be the equation y equal d. You can see that right here. The range will then go from d to infinity instead of from 0 to infinity. The domain does not change. Now let's talk about how to actually do the shifting. You want to start with the horizontal asymptote, which is going to be the constant added or subtracted to the exponential. It's going to shift it up if it's positive, down if it's negative. Go ahead and draw a dashed line wherever that happens to be. Here I have the equation 3 to the quantity x minus 5 plus 3. So plus 3 means I write the equation for y equals 3, but I make it a dashed line. That's the new horizontal asymptote. Now, what effect does the minus 5 have? It takes the original graph, which is 3 to the x, which you can see here in black, right here, and it's going to shift every point by point, 5 to the, yes, it's an x to x, so it does the opposite. It's actually going to move to the right 5. So each point, it's going to move right 5 and up 3. And this point, 0, 1, gets translated to the new point, 5, 4. And that's going to happen to each individual value. Now let's talk briefly about a vertical stretch or vertical compression. Vertical stretch or compression is where you're pulling on a thing like trapping one way or the other. A vertical stretch means you're basically taking the parent function, b to the x, like 2 to the x or 3 to the x, and you're multiplying it by a value greater than 1. If you multiply by a value greater than 1, it stretches the graph vertically, which means it goes up faster. So here, what you can see is the parent function, f of x equals 2 to the x, and then the vertical stretch 3 times 2 to the x. Right. That initial value is actually a vertical stretch or compression value. So if the value of A is positive and greater than 1, we have a vertical stretch. What does that do to every y coordinate? It takes every y coordinate, here a 1, and it multiplies it by 3, and so it becomes 3. Well, when I have 2 to the x, if I have x equal 1, I get the y value of 2. And it will take the 2, multiply by 3, and get me 6. So up here, I get the point 2, 6 on the vertical stretch. When we look at a vertical compression, again, the initial value is positive, but the number itself is a proper fraction. So it's between 0 and 1. And this is actually going to compress the graph, like you're pushing it down. It's going to widen out a little bit. You're shoving it down, so it goes out this way. And so it doesn't go up as fast, and this is by 1/3. So this is a compression by a factor of 1/3. So instead of crossing at 0, 1, it will now cross at 0, 1/3 of 1, which is 1/3. And again, this point here, which was at 1, 2, go ahead and write that down so you can see it, so it doesn't disappear on you. This becomes down here on the compressed graph, 1, 2/3. Take the old y value and I multiply by 1/3, and that gives the compressed y value. Now these graphs are not the same. They do not look the same. They are a distortion of the parent function. They're not stickers you're peeling off and placing somewhere else. When we're looking at stretches and compressions, as long as the A value is positive, then it's stretched vertically by a factor of A if A is greater than 1, and it's compressed if A is a proper fraction between 0 and 1. The y-intercept then will shift to 0A. but the horizontal asymptote does not change. It stays the x-axis, y equal to 0. So that's funny. And the range actually doesn't change. It goes 0 to infinity again, and the domain doesn't change. But what did change was just the y-intercept. Now let's talk about a reflection about the x-axis and about the y-axis. Reflections are like stickers again, but instead of just peeling it off and setting it down somewhere else, you're peeling it off, flipping it over, and setting it back down. Why are you flipping it over? The x-axis or the y-axis? So if we have a reflection about the x-axis, it makes the line a mirror image. So imagine painting this blue exponential 2 to the x with blue paint, and then folding the graph in half along the x-axis. And it's going to produce this mirror image, which is the red graph you see below, which is g of x equal negative 2. The negative is not a part of the 2. This represents down here a negative 1 times 2 to the x. And the exponential has to happen first, then you multiply by negative, which makes all the y values, you got it, negative. Well, that makes sense then. That just took the whole graph and reflected it over the x-axis. Now to reflect over the y-axis, we change the x from x to negative. So again, we start with the parent function that we have, which is y equal 2 to the x, which you see here. And to reflect about the y-axis, we then change the sign of the x variable, and it becomes 2 to the negative x, which actually can also be written as 1/2 to the x, because 2 to the negative 1 is 1/2. So again, it is a decay function. But writing it as 2 to the negative x is representing it as a horizontal reflection, reflecting it horizontally across the y-axis. And again, it's like you put a bunch of blue paint on there, and then you folded it, but this time on the y-axis, and it produces a mirror image, which is actually this red curve that you see here. So let me highlight the parts that are mirroring each other. So this part right here is mirroring this part right here. And this part here is mirroring that part here. And again, what we're doing is we're folding along the y-axis. That becomes a fold. Do a vertical reflection across the x-axis. Then the two parts that are mirror images of each other, well, it's just this, which is mirroring across to all of them, so that you can see the parts that are mirroring. Okay. Reflections of the parent function do change the value of the y-intercept. When you look at this, it reflected from 0, 1 to 0, negative 1. When you did this horizontal reflection across the y-axis, it did not change the y-intercept. So it only changes that when you're doing a reflection across the x. And to do that, you multiply the exponential by a negative 1. Now, that also changes the range to go from negative infinity to 0. It does not change the horizontal asymptote or the domain. So that's this one we're talking about. The range on the parent function goes from 0 to infinity, and the range on the translated or reflected function goes from negative infinity up to 0, but doesn't actually hit 0. Now let's look at this one right here. When we reflect across the y-axis, horizontal reflection, folding like this, then what we get is that the y-intercept does not change. The asymptote does not change. It's still y equal to 0. The range does not change. It's still 0 to infinity for both of these. And the domain does not change either. It's still 0 to or negative infinity to infinity. What does change is it changes from being increasing exponential to being decreasing or decay exponential. Let's put all the information together into this table that you see right here. So again, to shift it horizontally to the left, then we're going to have C plus C. If we want to shift horizontally to the right, minus C. This is assuming C is positive. To shift up, plus D. Down, minus D, assuming D is positive. Stretching, if the magnitude of the initial value is greater than 1, then you get a stretch. If it's between 0 and 1, you get a compression. Now, to reflect about the x-axis, to flip it over the x-axis, then you multiply the exponential by a -1. And to reflect about the y-axis horizontal, that means that you have b to the -x, which is the same as 1 over b to the x. This changes it from the parent function being a growth equation to the reflected function being a decay exponential, right? So here's a general equation for all of our different translated exponential functions. And now what we want to do is we want to go ahead and get into the homework problem. So go ahead and get your paper out and let's get started. Take a look at problem number 1. The graph of the parent function f of x equals 3 to the x is reflected across the x-axis, shifted downward 7 units, and then shifted left 2 units. Okay. Let g of x represent the new function. What is an equation? To reflect across the x means that you've taken all the positive y values and multiplied by a negative to get it to flip over the x-axis, because you have positive y above and negative y below. So the first thing we did was we took our 3 to the x and we multiplied it by a negative. That is going to change it. This to looking like this. Right? The next thing it says, shift it down by 7 units. Up and down affects y, but not x. It's not inside the exponential, it's outside the equation. So downward would be -7. So then I'm going to subtract 7. What's this doing? Well, right now it's been reflected, so it's crossing at 0, -1. So if I pull it down another 7, then it's going to be crossing way down here at 0, -8. Or 7, 8. So it's actually going to be crossing here, and my new horizontal asymptote is the dashed line y equals -7. So it's coming down and then it's coming like this. It's the same graph. It's just and then it's been shifted left to, oh boy, okay, really stretching it here. To go left means I do the opposite inside the exponential next to x. So if I want to go 2 units, but I want to go left, I need to add 2. So this is in the power x plus 2. So now I'm going to take this graph and I'm going to shift it to the left, which means that this point, which is now at 0, -8, is going to go left to -2, -8. So that's going to actually shift the graph over to the left. 5, 7, 8. And I've still got my horizontal asymptote at -7. But now this point right here is acting as the old intercept. So now it is at -2, -2. All right. So this is going to be a function, and this is going to be g of x. So what did it? I pulled it down by 7, and I shifted it left. What is the new y-intercept of g of x? Well, to find the new y-intercept, take this equation that you see up here, and we need to replace x So I'm trying to find what is g of 0, which is going to be a negative times 3 to the 0 plus 2 power minus 7, which is equal to negative times 3 squared, which becomes 9. So I have negative 9 minus 7, which is, whoa, that's negative 7. So it's coming down much slower. So the y-intercept is the ordered pair 0, negative 16. Remember, y-intercept is what's the domain of them? So I should kind of draw this in. So it's coming in like this, really steep. Now, when I'm looking at this, the domain, well, it's still stretching out and going forever, so it doesn't change. It's all real values, from negative infinity to infinity. What is the range? Well, now look at this down here. My horizontal asymptote is negative 7. That's sort of a ceiling. It can go above negative 7, but it can go down for it. So it comes from negative infinity and it comes up towards negative 7, but it never goes up into negative. So that's an open parenthesis round about negative 7. Now let's move on to a slightly different problem. This is the graph of negative 2 times 0.15 raised to x. So my multiplicative factor is the 0.15. Now, because that's between 0 and 1, that means that it is a decay function. But it's a decay function that's been reflected because of the negatives that it is reflected over the x-axis. Now they want g of x to be a reflection of this over the x-axis. So g of x is just going to be a double negative, or in other words, positive 2 times 0.15 to the x. So it shouldn't look like the one we have here, but every y value should get multiplied by a negative, so it actually becomes a positive. So where it's crossing right here at 0, negative 2, on the reflection, it's going to cross here at 0, 2. And this point right here, which is scooched out a little bit, 5, negative, is this 2, 4, 6, negative 6. And this is going to be 0.756 on the reflective one. So this will be up here. And so this one is going to come down like this. And you can see how they mirror each other. So we're looking for a graph that looks this. Has to go through 0, 2, because the reflective graph went through 0, negative 2. So we're looking for a graph like that. So this one doesn't go through 0, 2. This one does, and this one does. Choice A, that's and we know that it's got to be heading towards the right. Okay? Look at our graph here in P. And that eliminates this one, which actually got reflected across the x-axis. So B is definitely. So the question is it going to be B or C? They're both going to go down in the right direction. They're both crossing at 0, 2. But C is less steep than D. So let's take that other value that we used, which was about at point, whatever we want to call that, 0.756. So let's come out here. Let's go at about 0.75. Ooh, that's nowhere close to 6. 0.75. Yep, it looks like it. So B is going to be the first. Now we've already given the equation for G, and it's asking for the y-intercept, which we said was 0, 2. Equation was 2 times Is it 0.015 or 0.15? 0.15. Let's move on to the next problem. Now we're looking at problem number 3, which is very similar to problem number 2. We have the function f of x equal -5 times 0.25. Now we can also write this function f of x, 0.25 is 1/4. We can write this as 1/4 raised to the x. It's based on the parent function 1/4 to the x. It's been reflected and stretched by a factor of 5. It is normally an exponential decay function. So we can see here it's been reflected over the x-axis. You can see that it is down below, which is what happens when we multiply a negative. Now we want g of x to be the transformation of it. We want to move it up 5 and left. Okay, so up 5, left 5. Let's go ahead and try to graph what we've got here. So I'm going to take each point, left 5, left. So I'm going to start with this point right here, which is on my graph. This is when x is 0. X is 0, 1/4 is 0 is 1. So this is going to be 0, -5. Now where is that going to go? It's going to go up 5, which would put it here at the origin. Left 5, and my scale is by 2. So each bar gives a 2. So it's going to go over here. So it's going to end up over here at -5, 0. Going up 5, left 5. And that's what's going to happen to every single point. Up 5, left 5. Now let's take another value that looks, kind of where it's supposed to be. I could do x equal 1. When x equal 1 is equal by 4. So that's going to be this point right here. So when x is 1, I get -5 over 4, which is close to -1. So what's it going to do? It's going to shift up 5 to 6. But not up 5. So 5 minus 5/4 would be, oh gosh, 5 minus 4.25 is 3.75, right? So it's going to come up 5. So we're coming up. And that's 5, so about 3.25 and 75. And then we're going to be moving over to the left by 5. So we're going to come over, that's 1, and that's 3, and so we have this curve that's coming like this, and because we're up 5, our asymptote, our horizontal asymptote goes from y equals 0 to y. So that's going to be this line right here. So now we can look at this. It looks like it's going to be crossing somewhere close to 5, but not. So this is the line. That's going to shift up 5. And coming down here, this isn't close. This got shifted down, not up. This got reflected, and it didn't say reflected, right? It said up 5, left 5. So I think that both A are out. D doesn't look like an exponential. I don't know what's going on here on the left, but yeah, this doesn't look right at all. What about C? Well, it's got a horizontal asymptote at 5. It's crossing close to that. It looks like this point right here is -5, 0. Now we need to write the equation for g of x. Now what we're doing is we're taking this graph right here, which you can also write like this. And you want to so we can say that g of x got shifted up. So up by 5 is my x. And they're probably going to ask exactly what is the y-intercept. So then to find the y-intercept on the translation, what I'm going to do is I'm going to let x be 0, and I'm going to solve the exponential for y. So this gives me 1/4 to the 0 plus 5, then add 5 to that expression. So 1/4 to the 5 or 4 to the 5th is, what is 4 to the 5th? 4 to the 5th power is 1024. Yeah, that's pretty large. All right, so this is equal to, do this all correctly, that's okay. We have -5 divided by 1024 plus 5. All right, so -5 divided by 1024 plus 5, which is very close to this is a more exact value. And probably put in the approximation. Okay. Now, what is the horizontal asymptote of g of x? The horizontal asymptote, it got shifted up 5, so the horizontal asymptote is y equals 5. So another problem, let's see if we can get that one worked out. Now this one is a little bit different. It wants us to match the function to the equation. So we have to know what's growing and what's decaying. Whenever you have b greater than 1, it's growth, which means it generally goes up like this. And when b is between 0 and 1, it's decay, which means it generally comes down like this. So looking at this, I can tell that D, E, and F are growth equations, and A, B, and C are decay equations. So the ones that have a value for the growth factor, the multiplicative factor in here, the base of the exponential, greater than 1, have to be D, E, or F. So this one could be D, E, or F. This could be D, E, or F. And this could be D, E, or F. Now the ones that decays are going to be C. This could be A, B, or C. This could be A, B, or C because the rate is 0.81 and the rate here is 0.69, so it could be A, B, C. Possibilities. What else do we? Well, looking at the equations here, I can see that several of them have 2 as the initial value, and another couple have 4. That's going to change the y-intercept. So the y-intercept is going to be 2, or it's going to be 4. Now, there are 2 that are crossing above the other 2. That's C and D. Those have to be the ones that have an initial value of 4. So the initial values of 4 could be C or D. This then has to be, change colors, this then has to be D. Crossing at 4 and it's growing. Now this one is crossing at 4 and it's decaying. So it has to be C. Okay? Now the others are all crossing at 2. Now, if they're all crossing at 2, the only ones that cross at 2 are A, B, E, and F. So I can eliminate anything but A, B, E, or F. Now I need to figure out what they are, which ones are. So this one is crossing at 2, and it should be decaying. So compare A and B. Oh, they're both decaying and they're both crossing at 2. So that didn't help. Okay, well, let's look at the next one that has a value between 0 and 1. 2 times 0.81 to the x. So both of these are decaying. and they both are crossing at 2. This one and this one are both growth equations crossing it. So the one that has the larger multiplicative factor, that's closer to 1, since they're both less than 1, is growing more rapidly. That means it's steeper. So when I'm looking at the comparison between 0.69 to the x and 0.81 to the x, 0.81 to the x has to go up faster, right? Or rather come down. Okay. So when I'm looking at that particular one, the one with the smaller value is actually the one that can go up faster because that means that it's changing. And so the decay is going to have to be more like a larger denominator. The smaller the number, the larger the denominator, and that makes it go faster. So this one is going to be B, and this one is going to have to be A. So when the numbers change, it's going to change like that. And I'll show you some on Desmos in just a second so you can get a better feel for that. And then when I'm looking at these two, oh, well, I've already got those. Did I finish one? Oh, we've got 2 left. To the growth factors. With the growth factors, the larger the number, the faster it grows. So if the number is greater than 1, the bigger number grows faster. If the number is between 0 and 1, the smaller number grows. So comparing 1.59 to 1.28, 1.59 is bigger, so it's going to grow faster, so it's going to be steeper. So comparing E to F, E goes up faster, so this one has to be E, and this one has to be E. Now let's switch to Desmos. We're going to take a look at some different functions so that we can compare and see what's happening. All right, let me share that screen with you. I've grabbed some different exponentials with different bases, and you can see the effect it has on the graph. Let's look at the growth equations first. So these are the ones that have the equation or the base greater than 1. So 1.8 to the x, 1.4 to the x, and 1.1 to the x. They're color-coded, so the red ball here, 1.8 to the x, is the steeper one that we see coming right down here. Now 1.4 to the x, that's the next one that we see, to the next list. And 1.1 to the x doesn't even almost look exponential. It is if you scroll out far enough, you can see they all are. And you can see that the one that's going up the fastest is the one with the largest base. Now let's switch and let's look at the decay functions. So we're going to zoom back in, and we're going to look at our decay functions, which all have bases between 0 and 1, proper fractions. This is the opposite. The smaller the base between 0 and 1, the faster it grows. And that's because when you write these fractions, they have larger denominators. So this is 1 over 10, this becomes 4 over 5, and this becomes 3 over 5. Okay? So this one turns out to have a bigger magnitude. Okay? So when we're looking at these right here, what we see is that the red one actually has the steepest change, most rapid decay. And then the purple one, the 0.6x is next, and the 0.8x is the last. Now, let me come over here and write these down, 0.6x, 0.8x, and let me show you how you can tell by looking at the denominator. All right, let me reshare my other screen. So I think I said we have y equals 0.6 to the x, and we have y equals 0.8 to the x, and we have y equals 0.1 to the x. Now, if I write these fractions, I can write 0.6 as 6 over 10, or I can reduce that to 3/5. So this is the same as 3/5 to the x. And this is 8/10 or 4/5. So this becomes 4/5 to the x. And 0.1 is 1/10. So this becomes 1/10 to the x. Now, what we need to do is we need to have them all have one numerator. Right now, these two have a 3 and 4. So what I can do is I can divide by that value. So 1/5 divided by 1/3 divided by the reciprocal. So it's a weird thing, but it turns out that 1/5 divided by 1/3 is the same as 3/5. Right? So that 1/5 divided by 1/3. And then when I'm looking at this one, the 5 could actually be written in the bottom. Or another way of thinking of it is I could write this over the 2 of 5 to the 3rd. Thirds, and the 5/3 is smaller than 10. So the 10 is actually the one with the highest row. And again, 1/5 is the same as the thirds. We divide by fraction, we multiply by multiple. And this one, of course, could be written as 1/5, where this line in the center is the main division bar. And then this becomes 5/4. So then I'm comparing these together with the 10 that I have in the denominator. So this has the greatest change, one with the 10, then the 5/3, and then the 5/4. So decreasing values. Now, I'm not likely to ask you something like that, but just so you understand it. Let's move on and take a look at the next problem, which is problem number 5. So now we're going to look at problem number 5. Similar, but not the same as the one before. We have, again, some decay equations like A and B and C, and some growth equations like D, E, and F. When we're looking at these, thinking about what we did before, remember that for growth exponentials, the larger the base, the faster it grows, which means when I compare D, E, and F, D has the largest base. When we're looking at decay equations, it's the reverse. The smaller the number, the faster it changes. And that means that comparing A, B, and C, well, B looks like it's getting lower faster and going up faster. So B must have the smallest base. Now this says which has the largest value for B, it has to be one of the growth ones, because the decay ones, the value of B is between 0 and 1. So it's got to be one of the growth ones. It's got to be the growth one that changes the most rapidly, which is D. So coming down here, this is going to be D. Which graph has the smallest value? That's going to have to be one of the decays, where the value of B is between 0 and 1. And then it will be the one with the smallest base. It's the one that is changing the most rapidly. Is this of A, B, and C? That would be B. So this one is B. And then it asks which graph has the largest value for A and which one the smallest value. Now A is the initial value, which ends up being the y-intercept, unless it's been shifted left or right. So as long as it's only been shifted up or down, stretched or compressed, then that's the initial value. So for the largest initial value, we want to look at the y-axis and find the one that crosses the highest up. So when we're looking at these, that would be the value of C right here. So on the curve C. So even though it's a decay, it has the initial value. Now, which one has the smallest value for A? That would be the one that crosses the y-axis at the lowest point, which looks like this. Now let's look at problem number 6. We can see the graph of f of x equals 7 to the x in blue. The graph in red is a transformation. We want to write a function that describes the transformed function. First off, it's got to look like exactly the same shape, just reflected and shifted. So in this case, it's not been stretched or compressed. Those are very difficult to do. We won't have any of those. What we have is a reflection over the x-axis multiplied by a negative. And then that would have just reflected it to crossing it down. So that would have reflected it like this, right? But it got pulled down. So how much? Well, it looks like it got pulled down by 2. This would be crossing at 0, -1. But this one down here is definitely crossing at 0, -3. The difference between -1 and -3 is 2. So it got pulled down by 2. What did it cross the axis? So if f of x, well, let's do f of x in blue, keep our colors matched up. F of x is equal to 7 to the x. And then our g of x, which is the transformation, got reflected. And then it got pulled down by 2, which is 7 to the x power -2. Remember that negative on the 7 to the x happens after 7 to the power. All right. Now let's take a look at problem 7. We have the graph 3 to the x. Now remember that the graph of 3 to the x is going to cross the y-axis at 0, 1. And when x is 1, y is going to be 3. And when x is 2, y is going to be 9. 4, 5, 6, 7, 8, 9. This is going to be up here. And when it's at -1, it's going to be at 1/3, and then it's going to be at 1/9. So it the left and grows to the right. It's some kind of function. We want to know which of these pictures is 3 to the plus. So our h of x is a translation 3 to the x plus 3. This means it went up 3, which means that instead of crossing at 0, 1, it should cross at 0, 4. All right. And then instead of having y equals 0 as the horizontal asymptote, it should shift up 3. And so it should be at y equals 3. So I should basically have the same graph. I got a little wide there. Now, when I'm looking at these graphs, I'm looking for something that crosses at 0, 4 and approaches the horizontal line y equals 3 as x goes to -infinity. Neither of these satisfy the last one. So coming down here, well, this one approaches y equals -3, but this one approaches y equals 3, and it crosses at 1, 2, 3, 0, 4. So it's got to be a choice. Okay. Now, what is the horizontal asymptote of f of x? The horizontal asymptote of f of x, the original, is y equal to 0. This is y equals 0. And the domain of the original is -infinity to infinity. And the range goes from 0 to infinity. The normal function goes through 0 to 3. Again, I'm basing this on my understanding of what 3 to the x looks like, which is here. This is y equals 3 to the x. Okay, so you can see that the range is all the y values, and that's from 0 to infinity. The domain, you can use any x value you like, and the y-intercept is at 0, 1. And close parentheses there. Okay. So now we're going to go ahead and look at the other things that it wanted us to change. And those are, what is the horizontal asymptote of the translation? Well, when we translated it, we shifted it up 3. So the y asymptote, that horizontal asymptote shifted to y equals 3. Y equals 3. Oops, I should have done these in opposite colors. So this becomes oops, done in the same color. So y equals 3. The domain is still negative infinity to infinity. Look at this translated gray graph up here. It starts near 3 and goes up forever. So that's touch that asymptote. And then the y-intercept, of course, we said would be 0, 4. Now let's take a look at problem number 8. We have a graph of 5 to the x, and we want to know which shows the related function of 5 to the 4 plus. 4 plus x, swap a little bit. So let's go ahead and rewrite it in the normal way. So we've got f of x, which is equal to 5 to the x. So this one is going to grow very, very rapidly. Probably I should move this down. So 1, 2, 8, 5. So it's going to have a horizontal asymptote of y equals 0. It crosses here at 0, 1. And when x is 1, the y value is 5. So I've got 1, 5 on it as well. It grows really rapidly. When I'm looking at this, it grows very rapidly. And they want to know which of the following is the graph. 5, which would be 4 plus x. Now, when I write this down, I have 4 plus x. That looks a little weird that way. I can rewrite it as 5 to the x plus 4. Remember that this does the opposite. So this actually went left 4. Take this graph and I'm going to push the whole thing left. It's not going to change the horizontal asymptote, but it will change the y-intercept. So this point moves from 1, 5, and moving it left 4 moves it to negative 3, 5. So it comes to here, and the point that was at 0, 1 goes to negative 4, 1. So that moves over to here. So it's still approaching the axis. It's been shifted. I'm looking for something kind of like that. Now, clearly, A did not shift to the left, it shifted to the right. This one is. And then when I'm looking at B, is this a possibility? Well, let's see what it crosses through. It should be crossing now at negative 4, 1. And it should have the ordered pair for negative 3, 5. So when I'm looking at this one, that can come out, it's going by ones. 1, 2, 3, 1, 2, 3, 4. Ooh, that looks right on it. And then negative 4, 1, 1, 2, 3, 4. Ah, it looks like B is probably good. Let's check the other options. This one right here does not have it shifted up, and this one got shifted left, and this one got shifted down. So again, this has got to be our graph. It's got to be. Now it wants to know what is the horizontal asymptote of the original function. Right? So if we're looking at this part right here, when we're looking at this, the original function is 5 to the x, and h of x is 5 to the x plus 4. So 5 to the x has a range from 0 to infinity. The domain is all real numbers, and the y-intercept is 0, 1. So let's put that information in there. So the horizontal asymptote is still the x-axis. I'm trying to remember, I think I did that in right. So y equals 0, and the domain is negative infinity to infinity, and the range is 0 to infinity. with a y-intercept of 0, 1. Now when we shift it left forward, all the points got shifted left. The horizontal asymptote didn't change. It's still y equals 0. The domain is still negative infinity to infinity. The range is still 0 to infinity. But the y-intercept, I don't actually know what the y-intercept is. It's not even on my graph here or here. So how do I find it? In order to find it, I'm going to replace x with 0. So this gives me 5 to the 0 plus 4, which is 5 to the 4th, which is 625. And one that will show up on my graph. So the y-intercept is 0, way up there. So really, really fast. The larger the base, when it's greater than 1, the faster it grows. Okay, let's move on now to our next problem, number 9. We want to start with the parent function 5 to the x, and then we want to write a function, g of x, that results from a given transformation. We're going to take 5 to the x, and we want to shift it up. So g of x is just going to be equal to 5 to the x plus 3. That affects the y outside of that exponential, and it does what you think it's going to do because it's not on the same side of the other. Now we want to start back with x. So starting back with 5 to the x, shift down to. That's just 5 to the x minus 2. Now I'm going to start back with 5 to the x again. So I'm starting back with this 5 to the x. I want to shift it left. Left, I have to do the opposite. It's right next to that. So instead of minus, I'm going to. So this is going to give me 5. And I like to put these in front. X plus 1. And this one is all in the power. Now, starting back again with the parent function 5 to the x, shift right. So that's a 5. And instead of adding to go left, I'm going to subtract to go right. Now I want to reflect about the x-axis. So that reflects this way. So from positive y's to negative y's. So I'm going to put negative y's starting from the parent. I just multiply by negative 1. Now remember, this means that if you put 5 to the x first, all y values will be negative. Now to reflect about the x-axis or the y-axis, it would be horizontal reflection, which means that I have to change the sign on that. Starting with the original 5 to the x, this becomes 5 to the negative. That takes care of that problem. So we've only got 2 problems left. They're relatively short. These are just finding the value of a function. These are both exponential functions, and we just want to find the function value. So go ahead and pause the video, work out the responses, and then write yours down and turn the video back on so we can compare our answers. So how'd you do? Let's compare our answers. Remember, when you substitute the value of x, you're substituting into the power. So this is 6 to the 6 minus 2, or 6 to the 4th. Then we divide by 7. 6 to the 4th is 1,296 divided by 7 gives me about 185.1429 when I round up. Now on the next one, I'm looking for f of 5. So I take the exponential equation here. Notice that the power is a linear function of x. And I have 7 times the base 3 to the 5 minus 3 power, which is 2. So that gives me 3 squared, or 9. And 7 times 9 gives me 63. I hope that you've enjoyed this video and that you'll join me for the next video where we discuss logarithmic functions. See you soon.